should we continue? What comes next is the issue of anisotropy. And anisotropy is really the main reason why I think that the only way in which you can deal with crystalline materials is if you take into account the crystallinity. Of course, you are going to find a lot of continuum theories that try to describe the plastic behavior of a material using a continuum, effective stress theories. But the thing is, all the properties of the crystals, which are based on the crystallinity of the grain, are anisotropic. Elasticity is anisotropic, in some materials is heavily anisotropic, thermal expansion is anisotropic, plasticity is anisotropic, and also other properties like electrical and magnetic properties. So if you try to describe something which has different properties in different directions, you have to start thinking in terms of tensors. You cannot think in terms of a scalar describing the behavior. Yes, and then you put those crystals in an aggregate, and these crystals give the aggregate the distribution of the crystal, that is the texture, give the aggregate also anisotropic properties. So most of the examples that we are going to see here are based on cubic materials, which plastically are not so terribly anisotropic. But if you look into the distribution, there are examples for geological materials like olivine. There are examples for zirconium, for example, which is a hexagonal material, or magnesium. And you will see that things can be very, very different depending on the direction in which you are testing that material. So you really need to have a theory that is based on the crystal anisotropy. That's why we use polycrystal models, and that accounts for that anisotropy. So, as I say here, anisotropy is a direction-dependent response of the aggregate. That is, the same stress applied in different directions will give you different strains or different strain rates, for example. The tensors that describe this stimulus-response relation are in practically all crystals anisotropic. And for example, you're familiar with elasticity. In elasticity, we talk about the Young and the shear modulus for an elastically isotropic medium. So you have two constants. Now, in a cubic crystal, there are 3 elastic constants that are independent. In a hexagonal, there are 5, has axis symmetry. In an orthogonal polycrystal, such as uranium, for example, there are 9 independent elastic constants. That is talking about the elastic constants only. Now, if a property is anisotropic in the grains, and these grains have a distribution, then that property is also anisotropic in the polycrystal. In this case, the symmetry of the polycrystal is really given by the symmetry of the texture, not by the symmetry of the crystal. I come to explain. If the texture is invariant, for example, is something like that, independently of what are the crystals that give you this texture, what you can predict is that this is going to be a plane of symmetry. This is going to be a plane of symmetry. So this material is going to have orthotropic symmetry, independently of what are the crystals that constitute this material. Because anything that you do in that direction will be equivalent to doing it in that direction, or in this direction. So any of this, so the texture is what defines the symmetry of the aggregate. For example, an extruded polycrystal will have axial symmetry. So if you extrude the material, what you usually get is, if you extrude it through a hole, you have something that has axial symmetry. So this is the axial direction in the center, and you get something that has this symmetry. So this has 5 elastic constants, for example, associated with this symmetry. Now, the nice thing about polycrystal models is that they naturally capture the anisotropy of your aggregate, because polycrystal model is a collection of grains that with different orientations. And when you do an average of a property over all those grains, immediately that property will have the symmetry of the aggregate. So that is one of the advantages of using polycrystal models. For example, this case. This is copper. This is a simulation of rolled copper. We are again here looking at rolling textures. And one of the things that the code, the PSC, gives you is the evolution of the average elastic constants as a function of the formation. So in each incremental step, it calculates the elastic constants and puts that into a file that called elastothermal moduli. It also gives you the average of the thermal expansion coefficients. So if you look at copper is a cubic crystal. It has 3 independent elastic constants: C11, which is the same along this diagonal; C12, which is the same for the off-diagonal elements; and C44, which are the shears, the other 3 shears. So if you take averages for these textures of these constants, you find that C11, C22, and C33, they are the same at the beginning of the problem, because this is a random texture. Yes, you say, oh, they are not exactly equal. Well, because this is not exactly random, this texture. But if it were an exactly random texture, they would all coincide here. But as the formation proceeds and you go to 50%, 100%, and 200% deformation, see how C11, C22, and C33 evolve. So they differentiate from each other. The same with the constants C44, C55, C66. So these constants, now they are not equal anymore. So, and the same with the off-diagonal constants here, C12, C13, C23. So they evolve from a random texture into something that has 9 independent elastic constants. So this is one example of how texture and anisotropy are connected. So different mechanical regimes, I was talking about elasticity here, but different mechanical regimes have different properties, but all of those properties are anisotropic. As I said, elasticity, thermal, plastic, yes.
But it looks like C11, C22, C33.
Yes.
They are the same, right?
Yeah, if it is isotropic, then C11, C11, C22, and C33 here, they will be the same.
And the C12, C13, C23 will also be the same.
Yes.
But as texture develops, they are also becoming different.
Correct.
I see. So then the total number of independent components would be like 9 plus how?
No, 9. Orthotropic symmetry is 9 constant.
Okay. So 1, 1, 2, 2, 3, 3, and then 1, 2, 2, 3,
Yes,
3, 1, and there's symmetry there, and
Yeah,
then you will have 4, 4, 5, 5, 6, 6. These will be the 9
Yes,
independent.
this will be the 9. And here I indicated them as being different. Only the diagonals are the same. The off diagonals are the same, but there are 9 components. And if you do the calculation here, C44 in isotropy should be equal to C11 minus C12 over 2. That is in an isotropic material. That's in an isotropic material. So that constant over there, when it appears, that constant over here, C44, this value here for a random material should be equal to C11 minus C12 over 2. So I was talking about other regimes. So we have already looked at the elastic regime. In isotropic elasticity, you talk about the Young modulus and the shear modulus. And then you say, the tensile stress is proportional to the tensile strain. The shear strain is proportional to the shear stress. But in reality, in an isotropic elasticity, you have to use the Hooke law, which says the tensors sigma j, components of sigma j, are Cij KL epsilon KL. With viscosity is the same thing. The strain rate is proportional to the stress. This is the viscous modulus, but in reality, viscosity is also anisotropic. And when I say viscosity, we are going to be talking about viscoplasticity, because we are going to describe plasticity using a viscoplastic law, which is more like a creep type law. And so the Newton law is that gives this relation is also anisotropic. So here I just illustrated those regimes. And then you come to plasticity, and plasticity is not so easy. You don't have a law like that, the Newton law or the Hooke's law, where you can say, the strain rate is proportional to the stress. Plasticity is much more complex. And yes, people have tried to describe it with analytical expressions, but those expressions are always some approximation that is only valid under certain conditions for a certain state of the material. So in reality, those, in my view, it is better to bite the bullet and really go for a polycrystal description of plasticity. So the relation between stress and plastic strain rate, as I put there, is tensorial and is complex in the case of plasticity. Criterion that people uses and have used a lot is the criterion of the yield surface. So what is the yield surface? The yield surface is an idealization that says it's something that you define in the space of the stress components, and you say, okay, if all the points that are on a surface in the stress space are the points that, if the stress reaches that surface, then the material is going to relax plastically. So in principle, that is a useful concept. And in the case of polycrystal models, we can calculate these yield surfaces. We are going to do it. But first, let me tell you something. When they propose the idea of a yield surface, they have to assume a normality rule. The normality rule says that if I propose a yield surface, then when the stress touches a point in the yield surface, there is going to be a plastic strain rate, and furthermore, the plastic strain rate is going to be perpendicular. It's going to be perpendicular to the surface. So that is the normality rule, and is not something that you can physically demonstrate. You have to assume that is valid. With the polycrystal models, you don't need to assume that. You just say, okay, I'm going to impose stresses to my material, I'm going to calculate the strain, and I'm going to join all the points. That I get that way, and that will define my yield surface. So as I said, well, okay, the yield surface is the locus of stress state sigma ij in a 5-dimensional stress space. Why 5-dimensional stress space? Because the stress tensor has 9 components, but it is symmetric, so that leaves only 6 components, and the pressure is not supposed to affect the plastic deformation. Is going to be to some extent, independent of how much pressure you are putting. So that rules out one more component, that leaves only 5 independent components of stress. So that's why the yield surface is described in what is called the deviatoric space. That is the space where the pressure is not counted. So then it is assumed that there is a plastic potential, which is a function of the stress component, that accounts for a plastic energy rate, as an increase in the plastic potential is given by the strain rate times the increment in stress. And then, since it is also true mathematically that d phi is the derivative of phi with respect to sigma times d sigma, if this gives you the plastic dissipation, and this is mathematically what the function verifies, then you identify the gradient of this plastic potential with the strain rate. So you make that identification, which is this here, and then you assume that the yield surface is assumed to coincide with an equipotential defined by phi equal constant, and and because in mathematics, if you have an equipotential, if you have a potential field, any equipotential surface there is such that the gradient of the function is perpendicular to the equipotential surface. So because the gradient of the equipotential surface coincides with the strain rate, then you say, then the strain rate comes from a potential and is perpendicular to that yield surface. As I said, that is an assumption that does work, but it's not proven. So, for example, in the case of von Mises, von Mises is the simplest plastic potential that has been proposed. Von Mises says that the plastic potential is 3/2 of the sum of the squares of all the stress components, the deviatoric stress components. So you say if phi is equal constant, then that means that this function for any combination of this sigma ij has to be constant. So you look for what are all the sigma ij's that verify this relation, and that is what defines your yield surface. Now, if then you say that epsilon dot, that is the strain rate, is proportional to the gradient of this potential, you take the gradient and you get something like this, where the epsilon dot ij is collinear with sigma ij, and this is just a factor affecting it. So, in a way, what you are saying is that the von Mises criterion says is that the yield surface is, imagine a sphere in 5 dimensions, a sphere in 5 dimensions. The strain rate at the point where the stress touches the yield surface is the perpendicular to the sphere. Now Hill introduced the concept of an ellipsoid. So instead of this function, he proposes an ellipsoid in 5 dimensions that allows him to adjust, of course, better for anisotropy, and it has been used a lot, the Hill's ellipsoid, as a yield criterion. The problem with that, with this type of functions, is that you can adjust the parameters of those functions to a particular state of the material. When you start deforming the material and the texture starts evolving, also the anisotropy of the material evolves. So the ellipsoid parameters that you adjusted for a particular state of the material, they are not good 10% or 20% deformation further in the material. So it's really an empirical way of dealing with the problem, but not a physical way of dealing with the problem. Those coefficients in the Hill ellipsoid don't have a physical meaning, really. So that's why we are going to be, yes.
But if it is an ellipse, it will align only along the principal directions. At other places, the normal to the surface will be different from the direction in which.
Yeah, well, I'm going to do this in 2 dimensions, but let's say that that you have an ellipsoid, and this is sigma 1, and this is sigma 2. So if you say that the function phi is equal constant along this line, what it is telling you is that this stress state here will give you a strain rate that is perpendicular there.
Right.
Or if you impose the strain rate, say I impose a strain rate like this, then you have to look for a point where it is perpendicular here, and this is the stress that you are going to induce.
But in the principal one, they will both align with the same direction. In sigma 1 and sigma 2,
yes,
where you impose and where the strain rate, they will align. And if
well,
it
no,
is a sphere, it will align everywhere.
The stress is not aligned with the strain rate, as you can see here. They are not aligned. Only with
those two, right? Yeah.
Only when this becomes a sphere, then it coincides with von Mises, and then the perpendicular here makes the stress align with the strain rate.
Oh.
So this is the strain rate.
So I'm asking, in the case of ellipsoid, along the principal directions, this alignment would still be there, right? So along sigma 1 and sigma 2, when you apply stresses, The normal and the sigma directions are parallel.
When you say the sigma directions,
Sigma 1, for example, if it is the stress direction,
well, you mean
now you can see that normal,
yes,
right?
yes,
In
yes.
two directions they would still align, but rest of it will not align.
It will not, and it's good that you mentioned that, because the reason why Hill proposed the Hill ellipsoid was to deal with raw material, so material that had orthotropic symmetry. If the material doesn't have orthotropic symmetry, forget it. You cannot use the Hill ellipsoid, because it is not meant for material that doesn't have orthotropic symmetry. So he did it for raw material, and in raw material the symmetry is such that yes, you can count on orthotropy, unless something funny is happening. But if you have something, I don't know, like this, and you want stress or strain rate along this direction, because things are the same this way. This situation is as likely as this one, so none of them will take place. So as I said, that's why we now go into trying to describe plasticity, looking into really the mechanisms of plasticity. And the mechanisms of plasticity are propagation of dislocations, shear on crystallographic planes. And how does that happen? The dislocations are characterized by a normal to the crystallographic plane and a shear direction, the Burgers vector. For example, in FCC materials, the plane is the 1, 1, 1 plane, which is this one, and the dislocation shear along these diagonals, these three diagonals, the 1, 1, 0 directions. And what happens is, if you put the dislocation there, that dislocation slides, and it glides a bit further, and when it comes to the other side, what you end up having is a shear. If you imagine this situation happening in many places at the same time, essentially what you do is you shear your crystal along this crystallographic plane. Now, I'm going to show you that crystallographic shear induces crystal reorientation, and as a consequence, it induces texture evolution, because the texture is a manifestation of the orientation of the crystals. If you deform them plastically, they reorient. I'm going to show it, and then there's texture evolution associated with that. I don't want to dwell too much on this. You will look at it. When I give you the notes. But what this is the usual demonstration of how the tensors associated with the crystallographic plane are, or the vectors associated with the crystallographic plane are related with the tensors and the vectors in the crystal axis. So imagine that you have a crystal here. This is a crystal, and this is a slip plane inclined. There is a normal vector and there is a Burgers vector. If you define a reference system along those directions, and you shear here, the form of the strain tensor in the slip system is like this: gamma over 2, gamma over 2, and zeros. Okay. Now you say, what is the form of this tensor if I want to express it now in crystal axes, which are vertical and horizontal axes? So for that you have to transform this tensor from the slip system to the crystal axis, and that is done through a regular linear transformation matrix, which is this matrix R. And the way you build this matrix are, you build this matrix as the components of the Burgers vector, the components of the normal, and these are the components of the axis that is perpendicular to both of them. And then the linear transformation to put what is in the slip system, to put it into the crystal axis, is just this transformation. The repeated indices imply summation, okay? So in this particular case, because I only have epsilon 1, 2 and epsilon 2, 1, this becomes more simple. Only epsilon 1, 2 and epsilon 2, 1 appear in the expression. The others are all 0. And as it turns out, epsilon 1, 2 gives me, and that gives me Ri1, Rj2, but 1 and 2 are these two columns, so it gives me the components of the Burgers vector and the normal direction. So I get something that is like this: B, I, and J, B, J, and I times gamma over 2. So this tensor is called the Schmidt tensor, this tensor. It is telling me that the crystallographic strain in the crystal when there is a shear in a system is given by this tensor, Mij. So if I know that the system has shear in a particular plane, I calculate Mij, which is Bi and J, Bj and I, and I can calculate what is the strain in crystal axis. Once I have the strain in crystal axis, I can put them in sample axis, just doing another transformation. So we have this relation, and you can also show very easily that the result shear, if you apply the stress sigma in the crystal, you apply stress sigma in the crystal, the result shear in this plane is also given by the same Schmidt tensor. So tau is the result shear in this system is given by zero. So don't worry if this doesn't come through so easily, but what you have to remember is these expressions. These expressions, this is the definition of Schmidt tensor, and this is how a shear in a plane gives you the strain expressed in crystal axis or the result shear. There is something more. The trace of this tensor is 0 because the trace of this tensor is just the product of B times N and a scalar product, and since B and N are orthogonal to each other, the scalar product is 0. And so what that is telling us is that strain is incompressible. So if you add up the components epsilon 1, 1 here, epsilon 1, 1, epsilon 2, 2, and epsilon 3, 3, you get n1, 1 plus n2, 2 plus n3, 3 times gamma, but n1, 1 plus n2, 2 plus n3, 3 is 0, and so that is 0. We know that the trace of the strain is the dilatation, so there is no dilatation when you have plasticity. Yes?
The strain here will be related to movement of dislocations on the slip plane.
Yes.
The stress will come from where?
I haven't told you yet.
Okay.
but the only thing that I said is that if I apply a stress here to this crystal,
How will you transform it?
that will translate into a result shear tau in this system.
Okay.
And they are mediated by this equation.
Okay.
We still haven't talked about a constitutive law where we relate the stress and the strain. We still haven't done that. How much of one gives you so much of the other. So far it's just a kinematics. So far so good. If I now have a crystal and I'm pulling on a crystal, I'm not going to activate only one slip system. I'm going to activate more than one slip system depending if they are favorably oriented. The ones that are more favorably oriented for having a higher result shear will shear more, but others will also shear. So several of them will shear. So the total strain in the grain or the crystal, so far we are not talking about polycrystals yet, just single crystals or grains, is the sum over all the systems of all these expressions. So there is a gamma S on each system, and each of them will contribute to some amount of the strain component. The same with the strain rate. The strain rate is just the derivative of this, so epsilon dot and gamma dot. Now, let's assume that I want to enforce a certain strain or strain rate to my crystal. I say I want this crystal to deform with these components of strain. So, as I said before, the strain is a symmetric tensor, so it has 6 independent components. But because it is incompressible, the trace, that is epsilon 1, 1 plus epsilon 2, 2 plus epsilon 3, 3, has to be 0. So that gives me a further condition. So there are only 5 independent components. So if I impose an arbitrary incompressible strain to my crystal, what is the combination of shears in the different planes that are going to give me that imposed strain? Well, this is a linear equation, which means that for 5 independent components here, I need 5 independent shears. So that means that I need at least 5 slip planes to contribute in order to accommodate an arbitrary strain or an arbitrary strain rate. So 5 linear analytic systems are necessary to accommodate arbitrary strain rate. Now, FCC and BCC crystals exhibit at least 12 slip systems, so there is always a combination of 5 linearly independent systems that I can find. The hexagonals and crystals with lesser symmetry sometimes do not have 5 linearly independent systems. They are lacking those systems, so that is going to pose a problem that we will see later in the course how we deal with it. If you have a crystal here, that let's say that it can only shear on this plane. So this is a 101 plane. It can only shear in this plane and in this direction. So it will deform if you impose a shear like that. So if you pull on it like that, there is going to be a resolved shear here, and it will activate that. But the only thing that this will do is, if you look at it from here, yeah. If you look at it from here, is that what it will do is it will deform like this in that direction. That's the only thing that it can do. If you want to shear it in this direction, it will not shear. If you want to shear it in this direction, it will not shear. So only in this direction you can shear it. So that's what I mean. Some deformation modes will not be accommodated by only this system. And in general, you need 5 to accommodate a general apply deformation. So we are going to come to that in a moment. But what we are looking at now is that now the Schmidt law has to. I need to introduce the Schmidt law. What does the Schmidt law says? And now we are coming to your question. The Schmidt law says that a system is going to be active if a critical stress is achieved on that system. So you put shear, but it is not going to move the dislocations until a critical stress is achieved. When tau s is equal to tau critical, then the system is going to be active. If tau is lower than tau critical, the system is not going to be active, and tau cannot exceed the critical stress, because once you get there, you are active, and there is no way that you can exceed it. You just keep emitting dislocations. So this condition, then, from what I showed before, is that the condition that m times sigma equal to the critical has to be verified in 5 systems at the same time in order to accommodate a general deformation. Now, this is the equation of a plane. I don't know if you remember your geometrical analysis, but the equation of a plane, let's write it with mi xi equal d. This is the equation of a plane that defines the points that are at a distance d. The points that are at a distance d, the plane is at a distance d from the center, and any point here on this plane will verify this condition. So if this is x1, x2, x3, any point that is such that and besides m, actually, you usually see this equation like Ni. N is the normal to the plane. So this is the normal to the plane. D is the distance from the plane to the origin. So the scalar product between the normal and x equal d defines all the points that are on this plane. So any point that is on this plane verifies this condition. Any stress that is on this plane verifies this condition. But I need five of these conditions verified simultaneously. So what that means is that you need 5 planes to verify that condition, and that is the intersection of 5 planes. So that is the intersection of 5 planes. So I'm doing this here in 2 dimensions. So each slip system defines a plane. Tau 0 is the critical stress on that system. That is the distance to the origin. So each slip system defines a plane. And because the stress cannot exceed those planes, because once it touches them, it activates yield, the inner envelopes of all those planes is what defines a yield surface, okay? And the intersection, in this case, in a 2-dimensional problem, the intersection of 2 planes defines a point where the condition is verified on this system and on this system, in 2 systems simultaneously. In 5 dimensions, it has to be verified in 5 systems simultaneously. This is an example for a hexagonal material of the yield surface. As you can see, is much more irregular, but this is an example in 3D, in a 3-dimensional subspace of only 3 components, and this is prismatic slip and pyramidal slip plane. So here, all these points will activate 3 systems, at least. Some of them here, they will activate 4 systems, because the planes converge in 4 systems. And the other thing that is important is that, okay, can any vertex be active? And there is a principle of maximum work that it says that the vertex that is going to be activated is the one that maximizes the product of the stress times the strain rate tensor. So that means that as you can see, the one that fulfills that condition is when the strain rate is, you apply a certain strain rate, it has to be within the cone of normals of these 2 facets. If it is outside and you project this strain rate against this stress, which is the work, it will give you a lesser value than if you project this same strain rate against this stress. So the one that maximizes the plastic work is the one that is going to be picked. Now, there are several issues with this concept of a rigid plastic yield surface, that is a yield surface that is characterized by nothing happened, and suddenly, bam, you activate plasticity. In reality, it doesn't work that way. In reality, as you put more and more stress in your material, some dislocations start moving. And so there's not a well-defined point where if you move a bit away from it, nothing happens. And then you move a bit into it, and the dislocations start moving. So in reality, the dislocations move when the stresses, the result shears, are close to that critical value that I mentioned before. And so for that reason, this concept is not so, doesn't really capture the real behavior of the material, the ray-sensitive behavior of the material. And it also has other issues, which is if you have more than 5 systems converging into a plane, then you cannot solve an equation, a linear equation, where you have 6 equations or 7 or 8 equations and only 5 unknowns, which are the components of strain that you want to accommodate. So that ambiguity has been resolved by people doing different things, like picking at random 5 independent, or making an average of all the 5 independent systems, things like that. But and in addition to that, mathematically, it is very difficult to find convergence when you have something that has a discontinuity, such that the stress increases, and suddenly there is a discontinuity, and you have plasticity. So mathematically, finding convergence for those problems is more complicated. So the solution to that issue comes in the form of a rate sensitive law. So now, and we are getting into your question. Now we are relating rates with the stresses here. What the rate sensitive law says is that the shear rate on system S is proportional to the result shear. This is the result shear divided the threshold value to the power n. So that law says that gamma dot so this is the tau critical, and if the power is large, then that law says that this should be the gamma dot 0. That there is always some amount of shear when the tau result is lower than tau c, but only when you are approaching the critical value, you really start activating seriously that system. That's why this law is used with an exponent of usually n equal 20 or 30, which means that it's very flat and then it grows very rapidly. Now this gives continuity. This gives continuity to the problem, so we don't have that discontinuity that we had before. And so as I say here, gam dot is negligible unless tau s is near tau 0 when n is large. And of course, this is usually lower than tau 0, but now it doesn't have to be lower than tau 0 anymore. You can go a bit beyond that and be here, so you can be in a range here. And what that means is that if you look at the yield surface that I looked before, the faceted yield surface, this gives you a yield surface that is rounded and inside. And now getting the normal to this surface is straightforward. And there is a normal at every point. You don't need to look for 5 systems that are going to be within the cone of normals. It just comes naturally. When you solve the problem. That if you are here, the normal to this equipotential surface. This is not really a yield surface, it's an equipotential surface because you can have several of those surfaces as n increases. As n increases, you can have several of those surfaces. And these are equipotential surfaces, so epsilon dot times sigma equal constant. Now, if I apply a strain rate, then I have to find what is the stress that gives me that strain rate. This is a nonlinear equation, so there is no analytical solution, but there are very powerful methods and simple methods that, particularly, we use the Newton-Raphson method, which is a successive approximation method that solves this equation easily. So if you apply an arbitrary epsilon dot ij, you can find the stress that will give you that, according to this law. If you want to define a stress potential, you don't have to for the polycrystal model. You don't have to, but the stress potential will look something like this. So when you derive this potential, you get the epsilon dot given by this equation. So the plastic potential is defined this way. Is very straightforward. The solution is unique. Yes, the solution is unique.